All right, so in the last two lessons, we looked at a couple of transformations. We looked at shifts where we vertically or horizontally shifted or moved the graph up, down, left, right. Then in 30-2, we looked at vertical stretch and vertical shrink. So now we are going to look at reflections of the quadratic parent function, and then we're going to put all of these transformations together so that you can be sure that you can look at a graph or look at an equation and determine which transformations are present in that graph. So in number one, the quadratic parent function is graphed. We've seen this lots and lots of times over the last few lessons. We're going to graph g of x equals negative x squared on the same coordinate grid. So they didn't give us a t-chart here, but we can make our own. So just like we have many times before, I'll just make 3 columns. We've got x, and then we've got the parent graph f of x, and then we've got g of x. So if we, and it doesn't go up to 9, so we might as well just start at -2. So -2, -1, 0, 1, and 2. And we know that f of x would be 4, 1, 0, 1, 4. For g of x, the function is -1 times x squared. When there's a negative in front, that just means to multiply it by -1. So we take the f of x value and we multiply it by -1, which means we're just going to change the sign. So, of course, the opposite of 0 is still 0, so that one, the sign doesn't change. And now we have our t-chart for g of x. So as we plot this, -2, -4, -1, -1, 0, 0, 1, -1, and 2, -4. And here is our parabola. Compare g of x and its graph to the parent function f of x equals x squared. So here I would look at this and say that the graph is upside down, or it opens down, has the same width. So it's not skinnier or fatter like our vertical shrinks and stretches were. It's the same width, but it's just turned upside down. So here it tells us above number 3 that the change to the parent function there is a reflection over the x-axis. It's important when you list a reflection to tell what you're reflecting it over, just like it's important with a vertical stretch or shrink to say the factor of the stretch or the shrink. So this is a reflection over the x-axis, which just basically means it's a mirror image over the x-axis. It's like we flipped it upside down. It preserves the shape of the graph. So that's what we're saying about when I said that it had the same width. So how does the sign of a in the function affect the graph? So if a is positive, like it was in all of our transformations in 30-1 and 30-2, then the graph opens up. If a is negative, the graph opens down. Graph may represent more than one transformation of the graph of the parent function. The order in which multiple transformations are performed is determined by the order of operations as indicated in the equation. So how is the graph of f of x equals x squared transformed to produce the graph of g of x equals 2x squared minus 5? So this wants us to look at the equation and based on all the transformations that we've studied to say what's happening there. So this says that we have an a value of 2. we have a k value back from 30-1 of -5. So over in the margin, I want you to put a big star by this guy because this is our general form of a quadratic. We have y equals a times x minus h squared plus k. These are all the letters that we've talked about. If you go through your notes, we just talked about the sign of a here. Back in 30-2, we talked about if a is bigger than 1, then that has a vertical stretch, and if it's between 0 and 1, it's a vertical shrink. In 30-1, we talked about h and k. So just to kind of put it all together here, we know that if a is positive, it opens up. If a is negative, it opens down. Now, a also controls the vertical stretch or shrink, and now that we know it can be negative, now we use the absolute value. The absolute value of a is bigger than 1, meaning that we don't care about the sign. The sign is already telling us whether there's a reflection or not. But if it's bigger than 1, then that's a vertical stretch. And if the absolute value of a is between 0 and 1, then that's a vertical shrink. If we have an h value that's positive, that means we have a horizontal shift left. If h is negative in there, so like a minus there, then we have a horizontal shift right. If we have a k value that's positive, we have a vertical shift up. And if we have a negative k value, that means we have a vertical shift down. So when I look at this equation that they've given me and I compare it to my letters over here, I don't have anything in the parentheses with squared, so there is no h value here. The number in front of the squared term is multiplied, so that's an a value. It's 2, which is bigger than 1, so that means that value represents a vertical stretch. So I would say vertical stretch by a factor of 2 first. Then this -5, it's not inside the parentheses, it's outside, so it's a k value then. It's negative, so that means it represents a downshift. So vertical shift down 5. Use the transformations to graph the function. So we're just going to make ourselves a t-chart here. And so I've got x and g of x. Now, you could use the table for the parent function if you want. And I'm going to show you both ways so that way you can choose which way you want to do it. It really does not matter to me as long as you show your work and get the right answer. So I am going to write out the parent function chart that we've been using so much. But for g of x here, one way is to simply pick our values, so -2, -1, 0, 1, and 2, and plug them in. So 2 times x is -2 squared, and then -5, and then just simplify this using order of operations. So -2 squared is 4. 2 times 4 is 8, and 8 minus 5 gives me 3. So you could do it that way. I'm going to do one more like that. So we could do 2 times -1 squared minus 5. So order of operations, let's start with the exponent here. So -1 squared is 1. Then multiplication, 2 times 1 is 2. And then the subtraction, 2 minus 5 is -3. Now, the other option is to use the parent function. If I'm going to use the parent function, then what I'm doing here is I know that the x squared value is what's in this chart. And I'm going to multiply it by 2 and then subtract 5. So I could just do 2 times 0 minus 5. So 2 times 0 is 0 minus 5 is negative 5. Over here, the x squared value is 1, so it would be just 2 times 1 minus 5. Here, the x squared value is 4, so 2 times 4 minus 5. I don't care which way you do it. If you plug in the original x like this and put the squared in here, or if you're plugging in these values here. So that comes from over here. This guy comes from over there. So does not matter to me at all which way you do it. Whichever way makes the most sense to you is good for me. So this one does not say we have to graph the parent function, just the transformation. So we're just going to plot these points. So negative 2, 3, be right here. Negative 1, negative 3. 0, negative 5. 1, negative 3. And 2, 3. And so make sure the bottom is rounded. Don't let it be pointy. And there is our transformation. Now, after you graph it, compare it to make sure that it makes sense. I know that vertical stretches make the graph skinnier. So when I look at this, I should see a skinnier graph. Vertical shift, that means the vertex should have been moved down 5 units. Parent graph is at 0, 0. This is moved down 5. So you can always check to make sure that you've done it correctly. All right, number 6, how would you transform the graph of f of x equals x squared to produce this graph? So again, all I'm doing, and I'm going to scroll up so I can see it, is I'm looking at this right here. And I'm looking and I'm saying, okay, I've got an a value that's negative 1/2. So that's two things. Since it's negative, that means, and I should have written this, because the actual transformation, we don't say opens down, we say reflection in the x-axis. So because it's negative, one transformation is a reflection in or over, however you want to say it, over the x-axis. Because it's not just a negative 1, it's got a 1/2. A is between 0 and 1 when we take its absolute value, so there's also a vertical shrink. So vertical shrink by a factor of 1/2. We don't include the negative in the factors. The negative only has to do with reflection. And then I've got a +4. Again, that +4 is not inside parentheses, which means it's a k value. So this is a vertical shift up 4. So vertical shift up 4. Remember that shift and translation mean the same thing, so if you prefer the term translation, that's fine. So now we are going to graph this guy. So again, does not matter to me how you choose to do it. If you choose to do it making the table for the parent and then transforming it, or if you just choose to do the original. So I'm gonna make a 3 t-chart here, one for the parent and one for the new. So -2, -1, 0, 1, 2. So I know 4, 1, 0, 1, 4 for the parent. For h of x, if I'm using f of x, that means I would be taking the x squared value, which is 4, multiplying it by -1/2. I'm going to put the work over here. -1/2 times 4, and then adding 4. So -1/2 times 4 is -2, plus 4 is 2. Then for -1, the value of x squared is 1, so I've got -1/2 times 1, and then plus 4. So -1/2 plus 4 is positive 3.5. 0, -1/2 times 0 plus 4, which is 4. Now, if you were doing it the other way, I'm trying to do half and half, so no matter what you prefer, this was using the values of f of x. So I plugged the f of x value in for the squared term. We can also just plug in the original x values. So if I do that into my equation, I've got negative 1/2 times, and now my x is 1 squared plus 4. So 1 squared is 1, negative 1/2 times 1 is negative 1/2, plus 4 is 3.5. And when I do the same thing for 2, I square the 2 first to give me 4. Negative 1/2 times that is negative 2. Negative 2 plus 4 is 2. So these are my y values, these are my x values, so then I'm going to plot it. So negative 2, 2, negative 1, 3.5. So negative 1, 3.5, 0, 4, 1, 3.5, and then 2, 2. So vertex up here, making it round, connect the dots. It says identify the vertex and the axis of symmetry. So I think we can agree that the vertex is at 0, 4. Remember, the axis of symmetry is always x equals the x coordinate of the vertex. So x coordinate of the vertex is 0. All right, number 8, how would you transform the graph of the parent to produce this graph? So notice a lot of it's the same. It's got the negative 1/2 again, but this time the plus 4 is inside the parentheses. So inside the parentheses, that means that's an h value. It's a plus in there, so that means h plus values are horizontal shifts left. So the rest of it's going to be the same as what we just did here. We've got a reflection, we've got a vertical shrink, but now we've got a horizontal shift to the left. So we can basically copy what we did in the previous problem. We can say that we've got a reflection over the x-axis because of the negative. The 1/2 represents a vertical shrink by a factor of 1/2. And now this plus 4 that's an h value represents a horizontal shift left 4. All right, so now I want to actually graph it. Again, does not matter to me which method you choose to graph it. This time I'm going to do all the direct plug-in because when it's inside, I think that that's the easier method. When it's outside, it doesn't really matter so much, but I think direct plug-in is easier when you have an h value. So this one goes all the way over to the side here, so I'm going to start at negative 4, negative 3, negative 2, negative 1, 0, 1, and 2. Just trying to use the space that they've given us here. So I'm going to plug in my negative 4 in place of x in this equation. So I've got negative 1/2 times negative 4 plus 4 squared. Order of operations, I do inside the parentheses first. So that gives me 0. Then I do the exponent. 0 squared is 0. Then I multiply. Negative 1/2 times 0 is 0. Now I plug in negative 3. So negative 1/2 times negative 3 plus 4 squared. So I'm changing the value in the parentheses. It's going to go up by 1. So now instead of 0, it's 1. 1 squared also 1 times negative 1/2 is negative 1/2. Now I change it and I'm plugging in negative 2. So the number in the parentheses goes up by 1 again. 2 squared is 4. Negative 1/2 times 4 is negative 2. Now negative 1, negative 1/2 times negative 1 plus 4 squared. So that gives me 3 squared, which is 9. Negative 1/2 times 9 is negative 4.5. Plug in 0, negative 1/2 times 0 plus 4 squared. So 4 squared is 16. Negative 1/2 times 16 is negative 8. Now positive 1. Negative 1/2, 1 plus 4 squared. So 5 squared is 25 times negative 1/2 is negative 12.5. Now I plug in the 2. So 2 plus 4 is 6. 6 squared is 36. And then when I take half times negative 1/2, rather, all right, so we've got some very negative values over there. So when I go to plot these, negative 4, 0, negative 3, negative 1/2, negative 2, negative 2, negative 1, negative 4.5, 0, negative 8. Those are the only ones that would fit. But notice, I've only got one side of the parabola. All that means is that I really should pick some values on the other side also. So let's say I pick negative 5. If I add negative 5 in there, negative 1/2 times negative 5 plus 4 squared. Negative 5 plus 4 is negative 1. Negative 1 squared is 1 times negative 1/2 is negative 1/2. So this shows me that now I'm starting to come around the other side. So I don't need to continue the chart. I now know that I can use my symmetry to get these other matching points. So on the other side, should be down here, and then down here at negative 8 again. And make sure it's rounded and not pointy. And I've got my very pretty graph there. Identify the vertex and axis of symmetry. So I've got a vertex at negative 4, 0, and an axis of symmetry at x equals negative 4. Now, again, look back at the transformations. Reflection means it should open down. My graph does open down. Vertical shrink means it should be wider than the parent graph, which this is. And then a horizontal shift left 4 should move my vertex left 4, which it did. So I know that I've done this right because it matches up with the transformations that we know are true. Right under here, it just gives us what we already talked about, what we wrote in the margin. I didn't think it made sense to do the graphs without talking about this, so you can just see the margin. So this right here, we already did exactly what it asks for now in number 10. So this is, and that's why we put a star by it, this is of the utmost importance in this lesson. So we don't need to do that now. All right, we are not going to do number 11. I think we've done plenty of the examples of doing the graph, identifying the axis of symmetry, and all of that. So we are going to look at number 12. The vertex of the graph of the parent is at 0, 0. Describe how transformations can be used to describe or determine the vertex of the graph without actually graphing it. So think about how the vertex moves and which of those transformations move it. The vertex didn't get moved in lesson 30-2 when we did vertical shrinks and vertical stretches. The vertex moved in 30-1 when we had our shifts. So when we look at this format now, we know that horizontal shifts move the vertex left or right. We know that vertical shifts move the vertex up or down. So what's happening is that the x-coordinate of the vertex is going to be determined by my horizontal shift, which means h is the value of my x. Now notice that this is a minus So it's the opposite sign. So if this is a minus, then what we list as the coordinate is a positive because negatives move right. If this were a plus, we would list a negative value here because it would mean moving left. The K value keeps its sign, that's why it's a plus here, and that's the Y coordinate of the vertex. So that means that when we look at this one, minus H, so that means this is going to be a right shift. So right shift 4, so 4 will be the X coordinate. This is an up shift, so that would be 4, 7. Now, if there is no H value, if no H, then that means the X coordinate is 0. If there is no K value, that means the Y coordinate is 0. Because there are no shifts if the value is 0. So you're going to be working on these for your homework, determining the vertex. The last thing I want to do today is to look at example A. For the quadratic function shown in the graph, write the equation in standard form. So this goes through, and this is a very, very good checklist of steps. So you should be following this. This won't be in your homework until tomorrow because we're going to do another example of this tomorrow. But this is a very good checklist of exactly how we should find these values. So we're just going to do an example following these steps here. So we don't need to write down any steps. We're just going to look at this graph and try these A, write the equation in standard form. So first thing it says, step 1 is to identify the vertex. So we can say that my vertex is -2, -2. So we've got the values for that. We did that. HK, -2, -2. Now choose another point on the graph. XY, they chose 0, 3 here. So here, they've already labeled another point for us. So we're just going to say -1, 1 is my other point. Then it says substitute the known values. So when we use this general form that we wrote earlier, we are going to plug in the vertex is HK. So we're going to plug those values in for H and K. The other point we always plug in for X and Y. So what I would suggest is writing it out before you plug it in. So I would say H, because it moved left, that means that our H value is -2. Our K value moved down, so that's negative also. So H is -2, K is -2. Then my other point is my XY point. So X is going to be -1, Y is going to be +1. So now we use the same equation that we wrote before. So we're going to use Y equals A times X minus H squared plus K. And we're going to plug these values in. So in place of Y, I'm plugging in 1. So 1 equals A, I don't know, so that's going to stay A. Then X is -1, -1 minus H, which is -2, so minus -2, and then squared, and then plus K, so plus -2, which really just means minus. So now we're going to simplify. Inside the parentheses first, -1 minus -2. Minus negative becomes a plus, so I've got -1 plus 2, which is 1. So I've got 1 equals A times 1 squared, plus negative means minus, so that'll be -2. 1 squared is 1, so 1 times A is just A. And I've got 1 equals A minus 2. So if I'm solving for A, I would add 2 to both sides, and I've got A equals 3. So that means that if A equals 3, it says solve for A. So that's our step 4. So we did. Now we can write the equation of the function by substituting a, h, and k, not x and y, just a, h, and k. So I use the same format right here, and I'll pick a different color this time. Y equals a, which is 3, times x minus -2, which becomes a +2, squared, that's my h, plus k, so plus -2, which is -2. And now we have an equation for our parabola in transformation form. But it says to write it in standard form. So here's where what we did in Unit 4 comes back to us. Multiply and combine like terms to write it in standard form. So to write it in standard form means I'm going to need to square this. So square of a binomial pattern, remember, is square the front, so x squared. For the middle term, we multiply these together and then double it. So 2 times x is 2x. When we double that, that's 4x. And then square the back. 2 squared is 4. And I've got -2. So now I need to distribute. So multiply my 3 out. So 3x squared plus 12x plus 12, and then -2. These are like terms. So final answer, y equals 3x squared plus 12x plus 10. Now, you can check your answer. If you plug this into your graphing calculator, you should be able to look at it and make sure that it matches up with your parabola that you see in the picture. All right, we will do another of those tomorrow, so just hang tight for more examples on that, and your homework is on your syllabus.